Alright, so in this video we're going to look at something called traceable ring signatures, what they are and how they relate to signatures we might be familiar with from before. So we can start off by looking at what is a traditional signature, and there are multiple signature schemes for this, but in general you have some kind of message that you take the hash of, and then you generate a signature for that hash using a secret key and public key, and then other people afterwards, having only your public key, they can know that the corresponding secret key was used to create this signature. And that works pretty well, but what if we want to not know who in a group of people have signed something, but that someone in the group has signed something instead? That's where ring signatures come in. And basically, instead of having one public key, you now have a list of public keys. And you also use a secret key that corresponds to one of these public keys to sign the message hash. And the properties you get from this is that anyone in the group are able to prove that someone from within the group leaked some information or said some opinion or something like that, but it's impossible to tell which one of them did it. You will only know that one of them did it, but you can't know who. And then maybe this could be used in some kind of election, anonymous election, where you have a group of people that are supposed to vote, and then we can use ring signatures for people to vote anonymously. But then there's the problem, how do you prevent someone from voting twice? And that's where the next slide comes in, where we go from ring signatures to traceable ring signatures. And here we have this thing called a key image, which is the way that we prevent someone from being able to vote twice. So you can think of the key image as a secondary public key that you generate from a secret key and public key in a deterministic way, but people don't know that this key image, they don't know which of the public keys it corresponds to. But you have to publish this when you vote, and if you publish the same key image twice, then that's kind of proof that someone has tried to vote twice. So then you can choose what you want to do, if you want to accept only one of those votes, or what you want to do. Maybe you only accept the first one and you ignore attempts at voting later. Or you could also have a system where you can submit a vote multiple times and it's the latest one that counts. So basically you would be able to change your vote. That would also be an option, while still remaining anonymous with this scheme. A problem though is if you use the same key pair for multiple elections, your key image is also not going to change. So you can tell that, let's say, some unknown person in the first election voted for something, and then you can tell if they changed their vote or they didn't in the next election due to this key image that carries over. So you want to make sure you have a new key pair for every election that you're going to participate in. And yeah, so some of the properties we want in this key image is we want to know if a private key has been used twice, but we don't want to know which of the private keys has been used, which of the secret keys. And yeah, as I've mentioned previously here, you can think of the key image as a secondary public key that you can't tie back to another public key without knowing the private key. But somehow this works in the ring signature so that you can't cheat and make up a key image that doesn't have a private key in the signature. Not exactly sure how that works, but that could be something interesting to look into. And very important is that it's deterministically generated from the public-private key pair, which means from the same public-private key pair you can't generate two different key images. It's always going to be the same. And otherwise you could then just generate a new key image every time you want to vote, and you could vote multiple times. So it's important that it has this property that it's always going to be the same. And yeah, as mentioned here, if you publish the same key image twice with a signature, then other people can see that that you're trying to vote twice or change your vote or something like that. And something worth noting here is Monero is using traceable ring signatures. So this could, in theory, be a very good source for copying code. The only issue with this is that Monero uses something called ED-DSA for asymmetric cryptography, whilst Bitcoin Cash uses something called EC-DSA, as far as I know. And these are slightly different, so you probably need to adapt the cryptography to that. I have seen a Ruby library for doing what I think is traceable ring signatures on EC-DSA. So it could be very interesting to look into that if we're going to use traceable ring signatures on Bitcoin Cash for voting. And another interesting little thing here is how much space is it gonna take to store all of these votes. And that's something to note here, is that the more public keys you include in a ring signature, the bigger the signature itself is going to be. So you can see if we have a ring size of 3, then one signature is going to take up 240 bytes. Ring size of 6 means one signature is going to take up 432 bytes. And so these all fall on this line. So you can generalize with the formula here that the number of bytes is 48 plus 64 times n. For this is the size of a single signature. But since the signature has or since the ring has n participants, and every one of them are supposed to vote, that means that we have to multiply this by n to get what is the size of all of the signatures if we want to store all of them, not just one of them, but combined. And you can see that this is a quadratic formula because you have n times n. So that means this might not scale super well. If a ring becomes huge, then we might have an issue. So then maybe an idea here is to divide some kind of election into equally sized groups of some size. And then let's say the size is k and that we have n participants, then that means we have n divided by k groups. And you can see here that if we put this, or we multiply n over k with the formula where we substitute in k, the k's here will cancel and we get this expression, n times 48 plus 64k, as our formula for calculating the total space requirements for storing all of the keys in an election. So you can see here that the total number n here is the total number of people in the election, and k is the size of the groups used. And you can see that obviously the bigger the group sizes, the bigger the total amount of space needed to store all of the votes will also be. So we can do some practical examples of this. Let's say there's an election with 10,000 people, and we try to split it into groups of 1, 10, 100, 1,000, and 10,000, and look at how much space it takes up. So you can see that if, well, a ring size of 1 would be kind of a waste to use traceable ring signatures at all, so it's kind of meaningless, but it serves as a one end of the extreme spectrum here anyways. So you can see it takes 1 megabyte to store all of the votes if everyone just signs individually but using still the same algorithm of traceable ring signatures. So if you have 10 people in each group, you go up about 6.5 times to 6.5 megabytes. Basically, you can see from the substitution here that it's kind of like multiplying by 10 every time, but for the smaller numbers, this 48 here will have a bigger impact, so it's not quite as much as 10 in the beginning, but it approaches that. So ring size of 10, 6.5 megabytes, ring size of 100 meaning you have 100 groups of 100 people in each, is going to be 61.5 megabytes. 1000 per group means you only have 10 groups, it's going to be 610 megabytes. And if you try to put everyone into a single ring signature, then as you can see, it's close to 6 gigabytes of storage needed, which is maybe not ideal, at least if you want to store it directly on the blockchain. It would probably be very expensive to do that. So it might make sense to consider something like IPFS or some external storage solution where we don't need to actually store the votes on the Bitcoin Cash blockchain. But yeah, that's pretty much what I wanted to show in this video. So yeah.